So let's look at electrophilic aromatic substitutions. In chapter 15, we saw how aromatic carbon-carbon double bonds are less reactive than typical alkane double bonds. Consider a bromination reaction. We know that alkanes will undergo addition reactions. See, but arenes, no addition. Okay, and that's because they are very, very stable. They're very, very stable because they are aromatic. We have seen that aromaticity imparts significant stability to the molecule. So is a reaction a substitution, elimination, or addition, or pericyclic? Of course, we know that this is a substitution reaction. A substitution reaction whereby the benzene is the nucleophile while the bromine is the electrophile. Okay. Now, similar reactions occur for aromatic rings using other reagents. For instance, if you want to do a bromination, you can use bromine in iron 3 bromide as a Lewis acid. If you can do chlorination, use chlorine in aluminum chloride, or nitration, you use nitric acid in sulfuric acid, or sulfonation, you use fuming sulfuric acid, or the Fourier-Krauss reaction, in which you use RX and alkyl halide and aluminum chloride, or the Fourier-Krauss acylation, you use this acyl chloride in place of aluminum chloride. These are all examples of aromatic electrophilic aromatic substitution reactions. As you can see here, this is a bromination. A chlorination, nitration, sulfonation, alkylation, or an acylation. See? So again, this is a bromination, a chlorination, a nitration, a sulfonation, alkylation, and acylation. All these reactions are called electrophilic aromatic substitutions. Okay? Because we are substituting a hydrogen in the aromatic ring with an electrophile. So do you think an aromatic ring is more likely to act as a nucleophile electrophile? Of course, it's going to act as a nucleophile. Do you think the bromine is more likely to act as a nucleophile or an electrophile? Of course, it's going to act as an electrophile. Okay? We can see why shortly. To promote the electrophilic aromatic substitution reaction between benzene and bromine, we saw that iron is necessary. See, iron is necessary because iron can react with the bromine to give iron 3 bromide, right? And then in the presence of molecular bromine, this can react, and so you have an activated complex. Gives an activated complex which disintegrates to give a bromonium, or the brominium cation. Okay, this is your electrophile. Now, does this process make bromine a better or worse electrophile? It makes it a better electrophile. Okay. Now, the iron 3 bromide acts as a Lewis acid because you know it has empty low-lying d orbitals, so it can accept electron density. Aluminum tribromide or aluminum bromide is used sometimes instead of iron 3 bromide. A resonance stabilized carbocation is formed, which we call an uranium cation or a sigma complex. Make sure you note this name, the sigma complex. See? Okay, the sigma complex. This resonance stabilized sigma complex or uranium ion is then formed. And of course, this is what the hybrid looks like. Right. And then you can have the proton transfer and the restoration of aromaticity. Now, you can see that the iron 3 bromide acts as a catalyst here. It acts as a catalyst because it is regenerated. Okay, it's a catalyst because it is regenerated. Substitution occurs rather than addition. See, because the addition product gives an endothermic reaction, while the substitution gives an exothermic reaction because the huge electron activation energy for the formation of the uranium cation. See, so once you form the uranium cation, then it drops back to become aromatic, and you see, aromaticity here imparts significant stability. The restoration of aromaticity imparts significant stability. Okay, and that writes the reaction is exothermic. Chlorine can be used instead of bromine. Okay, but if you are going to use chlorine, you need to use aluminum chloride. Okay, and this is what the reaction is look like. Fluorination is generally too violent. Right, iodination is way too slow with very, very low yields. So this is what the mechanism will look like. So you have generated your activated. This is an activated electrophilic complex. Okay. Know that. Okay. Now, halogenation. Note the general electrophilic aromatic substitution mechanism. I'm going to attack there. This is a mechanism that you need to have in your cheat sheet. So you need to put this in your cheat sheet. Okay, cheat sheet. Put in your cheat sheet. Very important. And there are many different electrophiles that can be used to attack an aromatic ring. Okay, you can use fuming sulfuric acid if you want to get sulfonate, and you put a sulfonate there. See, this fuming sulfuric acid consists of sulfur trioxide gas and sulfuric acid. See, so if you look at SO3 in more detail, the sulfur double bond involves a p orbital overlap that's less effective. That's because you have a 3p versus a 2p overlap, so the overlap is inefficient, and so this is what the it's going to be, you're going to have something like this. Okay, we're going to have something like this. Now the sulfur atom in the sulfur trioxide carries a great deal of positive charge. See, carries a great deal of positive charge. Carries a great deal of positive charge. As we look here, if you put this, you have an oxygen here. One, two, like that. Then this is going to be positive and this is negative. 1, 2, 3, 4, 5. So this is what it's going to look like, because this, you're going to have a positive charge here. You have 1, 2, one more electron here. 1, 2, 3, 4, 5. So you're going to have a positive charge, and you're going to have this here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sulfur is, so you have a total of 24, but you have 6 valence electrons times 4 of them, so 6 times 4, 6 times 4 valence electrons, that's 24 electron pairs, 25 electrons, which is equal to 12 electron pairs. And you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. See? So it looks like this. So eventually what can happen is the attack by the nucleophile on the electrophile. And so it goes through all this. You see? And it continues. So in every electrophilic aromatic substitution mechanism, a proton transfer re-aromatizes the ring. Re-aromatizes the ring. And that brings significant stability, making the reaction exothermic overall. The spontaneity of sulfonation reaction depends on the concentration. Right? If you have a concentrated fuming sulfuric acid, you get sulfonation. But in presence of dilute sulfuric acid, you get a desulfonation. Make a note of this, is very important. Okay, it's very, very important. The other reaction is nitration. The mixture of sulfuric acid and nitric acid causes the ring to undergo nitration. See, and this is something we looked at already in lab. So you have the formation of the electrophile, generation of the electrophile. And this is a mechanism that you need to know. The nitronium ion is highly electrophilic. The ring attacks the nitronium ion. In the first step, the aromatic ring functions as a nucleophile, forming an intermediate sigma complex. And of course, that means that the sigma complex is stabilized by resonance. And then, as with any electrophilic aromatic substitution, the ring is re-aromatized via a proton transfer and restores aromaticity. So these are just the steps that you need to remember. Once the nitro group is formed, it can be reduced to the amino group using either iron or zinc or tin in HCl. Combining the reactions gives us two-step process for installing an amino acid. See, so first of all, you do a nitration, and then you do a reduction of the nitro group. Okay, so this is something you need to know. It's very important. You need to know this. Okay, now we're going to look at the Friedrich-Krauss reaction much later, but I think this is a good place to stop.